In the previous lecture, we have seen a few concepts introduced about high resolution imaging. We introduced the projected potential. We've also seen the objective lens as a kind of a phase modulator, and we understood that high resolution electron micrographs are actually phase contrast images. I will just revisit some of these concepts that were taught in the previous lecture again, and before we go to actually performing the analysis on the microscope, let me discuss these concepts in a little more detail so that you actually have a good clarity on how to interpret the data that you get from high resolution transmission electron micrographs. So let me recollect and show this image which I showed towards the end of the previous lecture. I'll bring three of these features together and show you. So the image onto your right is a high resolution electron micrograph from an aluminum sample oriented along the 001 zone axis, and what you see here, which appear like dots, are actually stacks of atomic columns. If you look at the image in the middle, what you have is you can consider the object as kind of a function which is represented by phi of r here, and then there is something called as the impulse response function. If you remember, I have given you an example of how an imaging device can modulate the information that you collect when you are recording some kind of an image. So this kind of a change which happens due to any recording medium can be called as an impulse response function. In a transmission electron microscope, we call this as a point spread function. Now this accounts for various factors which can actually cause this kind of a modulation of the information that you are actually recording. This gives you an idea of what really the object should look like and how does it get modified. Now, when I then see what is recorded on the screen, you can see that the image that is actually recorded is a convolution of the object function and the impulse response function or the point spread function. We introduced something called as the aberration function and a few other concepts in the previous lectures. We will look at them in a little more detail and figure out how these sort of high resolution electron micrographs are actually developed or how do they appear on the screen in the transmission electron microscope. On the image on complete left, you can actually see the ray diagram. This image I have taken from the paper from Dirk van Dijk. You can see that the specimen, if it is considered as some kind of a function f of x comma y, you have the exit wave from the specimen. It goes through the objective lens. If you remember in the very beginning the function of a lens, it is introduced that when I bring an object close to the focal plane on one side of the lens, the information I collect at the back focal plane can be related to the intensity on the object plane through a Fourier transform. So at the back focal plane, I first have the Fourier transform of whatever information I have from the exit wave, and I again have the inverse Fourier transform at the image plane. Now this image that is recorded is a convolution of the object function or the exit wave with the point spread function or the impulse response function in a broader sense. So the main message is high resolution electron micrographs are actually not really direct images of the atoms. So that is why when people compare HR-TEM versus HR-STEM, you would say that in HR-STEM you can actually get the exact position of the atom. If you remember the structure problem, we defined it as a threefold problem. So I know the unit cell parameters, I know the symmetry, and I know the position of the atom. And when I introduced this concept, I told you that the position of the atom can be obtained by the exit wave reconstruction through a through focus series. So what is important here is the image that you see here on the right, which appears like a periodic pattern, is not really the image of an individual atom, but if I consider these atoms are like scattering centers, if I isolate two exclusive atoms and then I start building on how the interference pattern is generated, I see some sort of a fringe pattern. We'll look at these in more detail as we go ahead in this lecture. But what you should remember is, when I see the electron waves that are scattered by the crystalline lattice, or in other words, when I have the object function or the exit wave function, this is actually modulating the phase of the electron beam that is incident on the sample. And then we introduce the concepts called as the phase object approximation. That is where we understood that the sample can modulate the phase, and we had the weak phase object approximation, and we introduced the contrast transfer function, where the contrast transfer function was defined as the imaginary part of the aberration function. Okay. So, we will now start seeing cases from two isolated scattering centers forming an interference pattern, and how do we get the intensity and the phase information from this when we are recording high resolution TEM images. So, what is important to note is, once again I re-stress this point, that these dots that you see in these kind of high resolution images are not really atoms, but this image that you see is sort of an interference pattern. So, let us now look at the origin of these lattice images. It may appear slightly repetitive, but I want to re-stress again and again on these concepts so that you do not make errors when you are looking at some information from an HRTEM micrograph. And bear in mind, there can also be errors because these are sort of the patterns generated based on the principle of interference. You might actually measure fringes which may not really correspond to physical lattice spaces also. These are the common errors you might run into, which I will summarize at a later stage. So, when an electron passes through the crystal, the transmitted beam and the diffracted beam. So, I am using this term called as transmitted beam, referencing to the beam which is actually along the principal axis of the electron microscope, that is the central undeviated beam. Some people call it as the unscattered beam. That is actually sort of wrong terminology. All the beams in fact are forward scattered and transmitted through the specimen. So, the transmitted beam and the diffracted beams coexist, and these recombine in the objective lens. So, if I think of the previous diagram that was shown, I have the exit wave, sort of a planar wavefront going through the objective lens. It recombines at the back focal plane, and then this propagates forward, and when I record on the image plane, when these waves that are going through this objective lens, they are actually interfering and they form some kind of a periodic spot pattern at the back focal plane, and from these again you have a reconstruction and you get the inverse Fourier transform of this information at the image plane. This was already introduced when I told you the concept of a lens. So, the interference between these diffraction spots, or from the forward scattered electron waves from the specimen, from the periodically arranged crystals, gives you a sort of a periodic intensity variation. So, these periodic variations appear as lattice fringes. So, the important insight here is the fringe spacing here actually corresponds to the reciprocal lattice vectors. That is, if you saw or if you recollect, the information at the back focal plane was also corresponding to the diffraction pattern, and when we introduced the stereographic projection and the Ewald sphere and so on, we linked these through the reciprocal lattice vector. So, you will see at a later stage that I can modify the object function that is written in spatial domain in x and y. I might actually represent them in some kind of a frequency domain of u and v as well. So, the interference patterns are actually reconstructed in the real space, but the reciprocal lattice vectors are in the Fourier space. So, the lattice fringes are essentially appearing from wave superposition. So, when I mean by superposition of waves, let us say I write psi 1 and psi 2 as two waves which are interfering, I can simply add them as psi 1 plus psi 2 in order to get the amplitude and the phase changes that are happening as a consequence of the superposition of these two waves. Okay. So, to understand these interference patterns that are generated in a HREM micrograph, there are certain theories called as the linear imaging theory versus the non-linear imaging theory. Let us understand the foundations of this concept. So, if you look at it, not all fringes that are recorded in an HREM micrograph actually correspond to real lattice planes. I will give you this with an example when I show you the concept of the reciprocal lattice vectors and I relate the lattice spacing to the modulus of the reciprocal lattice vector spacing as well. There are two possibilities. One is the interference between the forward scattered transmitted beam and assume that there is only one diffracted beam for the time being. You get some kind of a reliable structural information in this case. But when you have a realistic sample where the thickness of the specimen is not really very small, you do not have a sort of a weak phase object approximation. You have something called as the non-linear imaging theory, which also includes interference from half period fringes as well, and also accounts for various other factors such as dynamic scattering effects, which can lead to production of interference patterns which are not directly revealing the structural information. So, unless you know the thickness of the specimen and you do not know at what sort of focus the images are recorded and what sort of a spherical and chromatic aberration exists in the imaging system, there may be various factors which can modulate the phase of the object wave while it is propagating through a lens. So, the information you record cannot directly have a one-to-one correspondence with exact positions of the atoms. So, this brings back to my discussion on the first slide that we had. The HREM micrographs we see, which are represented as phase contrast image, which are appearing like lattice fringes, do not really give you exact positions of the atoms. If you remember in the previous lecture, I have shown you that when you change the focus of the objective lens, we saw from an amorphous area how the Fourier transform was actually changing and how the contrast of the image also changes. So, you really do not know from which position from the real specimen at which scattering center is contributing to the contrast you are recording in the image. Now, this gives you an opportunity that if I assume a specific model for the specimen here and I am orienting it in a zone axis, and from the other X-ray diffraction or neutron diffraction techniques if I vaguely have, and also from electron diffraction, if I know which of the crystal systems this particular specimen might belong to, I can come with a model, simulate an example HREM micrograph, check with how it matches with the really recorded image, record a focus series, and I also change the focus in the simulations that I get, and I can check if there is a one-to-one correspondence or iteratively repeat and then do a reconstruction of actual positions of the atoms as well. So, when I was talking about this changing of the focus, changing the contrast again, you should again recollect the idea that the objective lens, which is an electromagnetic lens, can alter the phase, and the lens also has inherently severe aberrations which also change the information that is actually propagated through the lens. This has effects mainly on the delocalization of the information that you are recording, and also the contrast as well changes. We have seen the example of how the contrast of the object wave changes through the contrast transfer function, which is the sinusoidal part or the imaginary part of the aberration function. And you also have the amplitude contrast transfer function, which I did not introduce earlier, which is the cosine part or the real part of the aberration function. So, let us try to understand what is the role of the objective lens again. The objective lens is non-neutral. It introduces some kind of a phase change to the electron wave that is propagating through the lens. But we saw that within the weak phase object approximation, the amplitude remained more or less unity. So the amplitude didn't change, but the phase changed significantly. That is why we were largely focusing on the phase part of the aberration function earlier. So the phase shift that the lens introduces depends on the spatial frequencies. So therefore, when I have an HREM micrograph, you have some lattice frequencies which are enhanced and some are sort of reversed, so they appear darker. So the ones which are enhanced start appearing like bright spots, and the ones which are sort of reversed appear as dark spots. And then changing the defocus can completely invert the contrast as well. I showed this example with just an amorphous area, but maybe later I will show you some simulation in one of the software on how changing the focus changes your contrast. So changing defocus can completely invert the contrast. So this sort of explains why HREM micrograph may actually show you sort of fringe spacing or information of sort of lattice fringes which potentially cannot exist physically within the crystal as well. So as an example, if I ask you to look at the lattice fringes from a simple cubic or a face-centered cubic sample oriented along 001 direction. In fact, I get the first diffraction spot as 200 when I am recording, when I am orienting the specimen along the 001 zone axis, and the 200 spot and the central beam together, if it is in a two beam sort of a condition, interfere together to form the micrograph. And physically, how do I understand this is something you have to start imagining how this 200 plane actually looks like within a face-centered cubic lattice. So in HREM micrograph, under special conditions, which is you should have a very thin specimen, because most of the ideas which are introduced were on the weak phase object approximation. When you orient the specimen exactly along the zone axis, in fact, when I was explaining you the recording of diffraction patterns, I have shown you that you may have more than one bright central spot. This actually happens when your orientation along the zone axis is not perfect. This can give you sort of interference patterns which you would not exactly correlate or comprehend with how the real lattice fringes from a periodic arranged atom should look like. You might see that there is this extra half fringe kind of a spacing which is appearing, or sometimes combining with the delocalization of information, you may see some strange artifacts that can appear in the micrographs as well. And we also saw the Scherzer defocus, where the differential of the lens aberration function was equated to 0, and we obtained the Scherzer defocus. When you are near the Scherzer defocus, you get the ideal contrast, and the imaging in such case becomes approximately linear. So what do I mean by this linear? I will show you the expansion of the image that you record. So the waveform of the image that is recorded I have shown you as a convolution of the object function and the aberration function, or the Fourier transform from the aberration function. And you can see that when I do an expansion of this complex waveform, it approximately can be represented with a linear summation, and you can ignore the higher order terms. So when I say that the imaging becomes approximately linear, I am sort of ignoring the higher order phase shifts that are caused because I am making it approximately close to the weak phase object approximation. So the hierarchy in understanding HREM micrographs is a crystal scatters the electrons. You call this as the exit wave. We have represented with the object function in the first slide schematic that is shown. The lens actually filters out spatial frequencies. If you remember in one of the very earlier lectures when we showed the Fourier transform and the spatial frequencies, we kind of related the resolution to the information that you're recording on the back focal plane. So we saw the band pass filters, how the high pass and the low pass filters work, and how the information on the image is changed. So the larger spatial frequencies the lens can allow, the better your image resolution is, and the interference from this actually forms the intensity of the image. So the image intensity actually can be considered as proportional to the projected crystal potential, and the atomic columns start appearing as the dots. We often call this as a structure image, but strictly speaking, this is not exact position of the atom alone. You should do a defocus series to exactly find out where in the crystalline lattice the atom is sitting. So HREM micrographs should always be interpreted through the imaging theory and not just visually. If I see a dot in an HREM micrograph, do not think that this is actually a position of an atom physically within the crystalline lattice. So going back to the whole discussion again, the origin of lattice fringes, if I think of something like interference from two simple wave vectors, people call this as the sort of a two-beam condition to start with to generate the interference pattern. If you think of the optics equivalent of the idea or the imaging theory that was developed for understanding HREM micrographs is the simple Young's double slit experiment. So if I have just two slits and there is an interference pattern produced, I see sort of a fringe pattern. So let us start with that kind of a simple thing. Let us say I have two electron waves from two atoms which are represented like this. Let us say I have two waves which have the form A1 exponential 2 pi I k1 dot r and A2 exponential 2 pi I k2 dot r. What I have written here is the summation of these two waves alone. In fact, if I have more than two, we have a summation and the whole theory is built on this. But to understand the foundations of this concept, let us start with the simplest case here. If I have two waves which are interfering and producing a sort of a fringe pattern, and I represent them with simple wave notation written in the exponential form. If I write this as the scattered wave as a consequence of superposition of these two waves, the intensity variation of this scattered wave, so if I write the intensity of this, it can be determined from multiplying this with its complex conjugate. So the intensity of this wave can be written as, so the intensity variation of this particular wave can be written as a product of the waves that are actually interfering times its complex conjugate, which can be simply written as this. Now if I do an expansion of product of these two together, it actually becomes like this: A1 star, I actually forgot to add the star here when I was writing this equation, but you would get an expression of this sort of a notation, and if I take the terms that are common and I simplify this, I can consider, let us say, this sort of fringe pattern is produced by summation of A1 e power 2 pi I k1. If you remember, in one of the very earlier lectures, we have written that k1 represents this and k2 represents this. The summation of these two, which appears like this, can be written as, just from multiplying this expression with its complex conjugate, I end up with the intensity variation as A1 square plus A2 square plus A1 A2 conjugate exponential look at this particular term here, K1 minus K2, and I also get this K2 minus K1. So the interference of these two waves together produces some kind of a periodic pattern like this, and the intensity variation of this can be represented by this sort of an equation. Now we've seen that when the crystal is oriented close to the zone axis, and when I consider that these two can also be represented in terms of the reciprocal lattice vectors, what I get here, the difference between K1 bar and K2 bar can be represented as the reciprocal lattice vector. Let us say I call it as reciprocal lattice vector G. It can be written in terms of K2 difference K1, and this expression, if I use the complex number notation on the Argand plane, if I write that Z is a complex number which has cos phi plus I sin phi kind of a notation, and I use this Z plus Z star, which is the thing here, I can modify this expression as A1 square plus A2 square plus 2 A1 A2 times cosine of this K1 minus K2 and dot product of R. And we've written this is also your reciprocal lattice vector as well. So what you get is the interference produces contrast variation as a function of the cosine of a reciprocal lattice vector and the dot product of the position vector as well. So you get a cosine modulation of the amplitude that you record in the HREM micrograph, and the fringe spacing can be determined from the difference of these K1 and K2. So what does this tell us? If I take two simple scattering centers which are separated, so let me call this as 0 and this is some G bar and this is K1 and K2 here. When these two are interfering to produce a fringe pattern like this, the difference between this K1 and K2 corresponds to my reciprocal lattice vector, and the fringe spacing is inversely proportional to the modulus of this reciprocal lattice vector. We will see how this modifies if I introduce the third term. So if I call this as G plus, and if I call this reciprocal vector on the other side as G minus, let us try to understand how this D changes. It is in fact rather straightforward. So if I have these three terms here, I have K1 minus K2, and let me call this as K2 bar here. I end up with the D is proportional to 2G, and this gives me a fringe spacing of D over 2. So what exactly I am trying to tell you here is, from a sort of a two beam interference condition, I get direct measurement of the fringe spacing, but in reality when I have more than two beams, the third beam that comes in, it actually corresponds to these two reciprocal lattice vectors together, and when I use this inverse relationship, I end up getting half the lattice fringe spacing, which in most cases physically is not difficult to comprehend from a direct image. So this brings back to my earlier point, do not directly represent, or do not, unless you are completely sure about the sample in which zone axis and what are the allowed reflections and so on, you cannot measure any fringe spacing and you cannot relate it to the actual physical lattice spacings as well. So you have to be very careful while interpreting the HREM micrographs. So if you look at how this mathematical reconstruction that is written here appears physically within the microscope, when I have a crystalline specimen, the forward scattered electrons actually go through the objective lens. At the back focal plane, I see a sort of a spot array, and depending on the resolution of my imaging system or in the microscope that I have, and sometimes you can think of putting in an aperture to restrict the information that you get. This is what you do for selected area diffraction, but the farthest spot that actually appears corresponds to the the resolution of the image that you are actually recording. And this is sort of, if I call this as psi e as the exit wave, I get the Fourier transform of the exit wave here, and I get the inverse Fourier transform convoluted with the aberration function. And so this already contains my object wave. So this is what you are actually recording in an HREM micrograph. So if I look at another schematic representation of this, the incident electrons, when they are diffracted by a crystal which is oriented exactly along the zone axis, the angle of scatter that you have here can be related through the Bragg angle, and when they actually go through the objective lens, they form a periodic diffraction pattern at the backfocal plane, and these again interfere to form a sort of a fringe pattern which corresponds to the information you record in an HREM micrograph at the image plane. And to understand this and to simply look at a two beam kind of a condition, this is not the same two beam that we talk about when you are trying to image dislocations or some of the defects. This is the two beam sort of reconstruction or superposition phenomena that I described in the previous slide to understand how the fringe spacing is appearing in an HREM micrograph. So let us say the beam that is scattered at an angle of 2 theta HKL is interfering with my forward scattered electron beam, which is along the principal axis. I produce this sort of a fringe pattern here, and I can represent the propagating wave fronts with two of the propagation vectors on the Ewald sphere, and the difference between these two corresponds to my reciprocal lattice spacing. In fact, this is what I was trying to tell you on the previous slide as well. So the cosine modulation of the amplitude that I record in the HREM micrographs is proportional to the fringe spacing, or inversely proportional to the reciprocal lattice vector that is actually giving this kind of fringe pattern. So this makes it extremely important that in order to record this sort of high resolution information, it is imperative that you orient your specimen precisely along the crystalline zone axis, and then the lattice images that are arising are actually a consequence of the interference between the forward scattered electron beams. So to look at the final intensity that you are recording, this is what we showed in the previous slide as well. The amplitude that is recorded, or the intensity of the HREM micrograph, is A1 square plus A2 square plus 2 times A1 A2 and cosine of G dot R. What is important here is the phase of the electron wave is modulated by the lens aberrations, and in the intensity recording from a single image, you are only getting the intensity variation but not any phase information. So the phase information you can retrieve by actually changing the defocus values slightly. That is what we saw in the lens aberration function, and from this you can understand how the phase is also modulating the information that is recorded in an HREM micrograph. So going back to the concept called as linear imaging theory, which is used to simplify and understand how the contrast variations within an HREM micrograph are, for very thin specimens, you can assume that the electrons mainly experience only phase modulation. This is what is called as the weak phase object approximation. That is because when you write a Taylor series expansion of the wave function that you have, you can ignore most of the higher order terms. So you have some kind of a unity or a constant plus some kind of an imaginary part of the the aberration function as well. So mainly the phase modulation caused by the aberrations from the objective lens result in this sort of the fringe patterns that you are getting. So if I take the projected potential as Vp and I have the interaction constant, we'll look at how this interaction constant looks like in some of the latest slides. You can expand this complex number by taking this kind of a linear expansion. So if this has the notation e to the ix, I can simply write it as 1 plus ix, and this becomes the imaginary part. So if I write this as cos of ix plus cos of x plus I sin x, the imaginary part, which is the sinusoidal form of this particular function, gives me the information on the phase modulation, and this was actually called as the contrast transfer function, or specifically the phase contrast transfer function. And the interpretation is the constant term that I have here corresponds to the central beam. The linear term completely corresponds to the entire scattered information, and this sort of simplification of the complex number to understand and interpret the intensity and the phase modulations that are resulting through HREM micrograph is actually called as the linear imaging theory. Now, I told you that the objective lens is sort of acting as a phase modulator. So let us understand or revisit the foundations of what we introduced with the objective lens and how the phase is varied in the next slide. So if I have an objective lens like this, the information that goes through my objective lens first appears at the back focal plane through a Fourier transform, and then through another inverse Fourier transform I get the information at the image plane. So the exit wave, which is represented by this kind of a complex number, goes through the lens, and what is important to note is the objective lens is modifying the phase of the spatial frequencies. This xy terms that I write here, if I write it in terms of the frequency term called as u, what I record at the back focal plane is in terms of the frequencies that I actually record, and from these, if I introduce the point spread function or the aberration function of the imaging system, I am sort of multiplying this information of the exit wave with the aberration or the impulse response function or the transfer function. Sometimes you term it as lens transfer function, sometimes you call it as the impulse response function. You also have the MTF, you call it a CTF. The point is, all the aberrations and all the factors that can actually modify the phase of the object wave due to the imaging system can all be multiplied with this information of the projected potential, and when I am multiplying two functions, I represent it with a convolution. So the other term, that was the lens imperfections. So if I look at the lens imperfections in terms of the spatial frequencies, so the image function looks like this, and the lens imperfections are represented by this term, and this accounts for the defocus as well as the spherical aberration. And if I take the cosine, it actually gives me the amplitude contrast transfer function, and if I take the sine of this particular complex expansion, I get the phase contrast transfer function. And the image intensity that I record, I was just telling you that is a sort of a multiplication. When I multiply two functions, I call it as the convolution. So the image intensity I record in an HREM micrograph is proportional to this kind of a term, and what we have done here is simply taken the linear imaging theory simplifications and we have written a simple mathematical expansion or a summation of a unity plus the convolution or the complex number that we had here. So, the image intensity that is recorded for very thin specimens can be represented this way. So, this is what you get in an HREM micrograph. So, I think before we move further and understand how this changes, this is perhaps a good point to stop and summarize that the information you record in HREM micrographs is a consequence of interaction of multiply forward scattered electron waves from a crystalline specimen, and you get a sort of a fringe pattern. And remember that the fringes that you are recording are not directly corresponding to lattice fringes always. There could be cases where when it is actually matching with directly the reciprocal lattice vector which is producing these fringes, I can sort of relate it to the structural information I get, but it is not always the case. So, remember under which sort of conditions you are recording the information and what these fringe patterns actually correspond to.